Hello everyone, my name is Zhao, and in the next 10 minutes, I would like to discuss how to improve the blending efficiency for run-of-the-mine stockpiles through generating nearly real-time 3D multi-layered room stockpile models. At Permanent Hill, there are 3 stockpiling locations: in-pit, open pit, and room stockyard. At moment, all mined from the underground stope will be stockpiled at the in-pit location first, and then transport to the room stockyard using load and haul operations. The open pit mining was completed. No new material will be stacked onto the open pit stockyard, but materials at the open pit will be reclaimed and transported to the room stockyard. Most all at room stockyard will be sent to the crusher directly for production, but some stockpiles need to be cleaned in advance because they contain some structuring materials. These 2 images were taken by me on the field trip to the Permanent Hill. Stacking and reclaiming operations both are 24 hours per day for almost 365 days per year. Clearly, these operations change the stockpile shapes and quality distributions. Now ask yourself, what if we use room stockpiles for blending or quality control? Obviously, stockpiles can be used for blending because it happens naturally during the stacking and reclaiming operations. However, efficient and effective blending is almost impossible because the most accurate quality information is not available in real time. There is a lag of around 12 to 24 hours to obtain the assay results from the samples. Furthermore, the quality of a stockpile is calculated as a weight percentage of each element and is saved as a table in the current management system. As a result, even mine geologists don't know the quality of the ore received at the crusher. If we can have the most accurate quality and quality distribution within a stockpile and extend such understanding to all the room stockpiles, it is then possible to apply the optimization algorithms at different stages. For example, to stack on selectively to adjust the quality of stockpiles, or to reclaim stockpiles proactively to meet the required quality and quantity combinations. Thus, the blending efficiency will be improved dramatically. My project aims to build 3D stockpile models to reduce the impact of the delay in receiving the assay result. A 3D model of a stockpile is generated based on a stacking location. Such a 3D model can retain the quality information when the quality assay results are available. Also, a 3D model may contain multiple layers if the same stacking location is used, and the qualities of the material in these layers can be different. Furthermore, all these 3D stockpile models can be updated based on reclaiming locations and the kinematic model of a front wheel loader. Last, these 3D models will be calibrated using the monthly laser scanning model to improve accuracy. Knowing the quality and quality distribution among stockpiles, I would like to integrate the optimization algorithms developed in another project to demonstrate how to achieve proactive reclamation. Summarize the 3 contributions for my project. First, improved data usage. I only need current available information for stockpile modeling. No extra hardware or dataset is required. Second, such 3D model will improve the blending efficiency because these models allowed optimizations to be conducted during the handling or rehandling processes. Last, reduce the cost. Normally, the supplied quality is always better than the required quality. If we have better understanding about the quality of the stockpiles, we can control the margin and thus reduce the cost. The following steps were used to create 3D stockpile models. First, I merged laser scanning data to generate a base with a resolution of 1 meter by 1 meter. Second, I extract the stacking locations and the tonnage from the dataset saved in the fleet management system. This is because my translation partner, Eka, has the technique to generate 3D stockpile models based on the stacking locations and tonnage. Third, I map the quality information from the sampling result to layers, or to the models. Last, I extract the boundaries of the stockyard models using a fuzzy logic algorithm for future reconciliations. This animation shows 3D stockpile models generated based on the stacking locations and the tonnages on top of the base. I prepared this image using MATLAB, and all the models are assumed to have ideal cone shapes. It is also worth to mention that my translation partner, Eka, has a better algorithm to generate these 3D models. To calculate the quality of reclaimed material, I create a kinematics model of a front wheel loader. The moving path of the bucket in 3D can be approximated by the kinematic model. Adjust the control parameters of the kinematic model will generate different paths. The intersection between the stockpile model and moving path will generate a cut, which is named as a voxel in this project. A voxel may contain materials from many layers. Applying this kinematics model to different locations, we can voxelate a stockpile. The quality and the quantity of every voxel can be calculated because we know its shape and quality of the material inside it. The research project number 5 has developed a number of optimization algorithms to achieve the required quality and quantity combinations under the minimal reclaiming time. All these algorithms were embedded and are represented as the purple box in this image. The optimization system contains the following inputs: the quality and quantity information for every voxel. Although there is only one voxelated stockpile showing in the image, we can voxelate multiple stockpiles. Operational constraints, including the precedence and safety. The precedence constraint indicates the order of the reclamation. For example, to reclaim a voxel from the lower batch, the voxel on top of it has to be removed first. We also have the recurring cost for each reclaiming operation as the constraint, plus the delivery requirements, which means the quality and quantity required. I'm currently working closely with my translation and end-use partners to build a such demonstration system to conclude this project. So far, I have one journal paper published. I believe there will be another journal paper publication before the end of this project. At last, I would like to say thank you to my supervisor, my end-use partner, and my translation partner, as well as the state government of South Australia. Thanks for your support. Thanks for your patience. This is the end of my presentation.